In Fabric, consensus is not mining. A transaction moves through proposal, endorsement, ordering, validation, and commit. By separating these steps, Fabric separates trust, scale, and governance, so enterprises can agree on shared data without exposing everything to everyone. So far, we've covered the building blocks: organizations, identities, peers, ordering services, chain code, ledgers, and channels. Now we'll look at how those parts work together. A client submits a proposal, peers simulate and endorse it. The ordering service sequences it, and peers commit valid results to the ledger. This transaction lifecycle is where Fabric's architecture becomes practical, and it sets up the next topic: confidentiality and private data. A Fabric transaction is handled in stages rather than executed everywhere at once. The client sends a proposal to the required endorsing peers. Those peers simulate the chain code, sign the result, and return endorsements. The ordering service then batches endorsed transactions and establishes their sequence. Finally, committing peers validate the endorsement policy and version checks before writing valid transactions to the ledger and updating world state. The key design shift is that Fabric executes before it orders. Endorsing peers first simulate the proposal without updating the ledger and produce a read-write set. The ordering service then creates one agreed sequence of transactions. Committing peers later validate that the endorsements satisfy policy and that the data read during simulation is still current. Only valid transactions are committed. This separation helps Fabric scale, supports different ordering services, and gives enterprises tighter control. In many blockchains, ordering comes first. Once a transaction is placed in the log, every validating node executes the same smart contract, even when only a few organizations are involved. Fabric avoids that pattern. Required endorsing peers simulate the transaction first, based on policy. Then the transaction is ordered and validated before commit. The result is less wasted execution, with stronger support for confidentiality and enterprise governance. The lifecycle begins when the client application prepares a transaction proposal through the Fabric Gateway or SDK. This proposal is not yet the transaction being committed. It is a request to simulate a chain code invocation, including the chain code name, function, arguments, channel, and the client's identity. The client sends the proposal to the endorsing peers required by policy. At this point, peers can evaluate it, but the ledger remains unchanged. During endorsement, each required peer receives the same transaction proposal. Each peer runs the chain code independently against its current world state. This is only a simulation. The peer calculates what would be read and written, but does not update the ledger. It returns the result, the read-write set, and its signature. The client then checks that the required endorsements match before the transaction moves forward. The simulation produces the evidence Fabric will validate later. The read set records each key the transaction depended on, along with the version seen at that moment. The write set records what the transaction intends to do: update, insert, or delete keys. These sets come back in the endorsement response. During validation, peers compare the recorded versions with current state. If anything has changed, the transaction is rejected before commit. Endorsement policy defines whose approval is required before a transaction can proceed. In this example, the policy is an AND condition, so both org1 and org2 must sign. The client gathers matching endorsement responses, then submits the transaction to the ordering service. Ordering does not evaluate the policy. Later, validating peers check the signatures, payload consistency, and client identity before accepting the transaction. Endorsement depends on every endorsing peer reaching the same answer from the same proposal. If one peer writes A as 60 and another writes A as 65, the endorsements do not agree, even if both peers ran valid chain code. That is why chain code must avoid randomness, local clocks, and uncontrolled external calls during simulation. Any needed value, such as a timestamp, should come from the transaction input and be validated consistently by all peers. Once the client has enough valid endorsements, it packages the proposal response into a transaction envelope and sends it to the ordering service. Ordering nodes do not run chain code, recheck business rules, or decide whether the transaction is valid. Their job is narrower but critical. Agree on one sequence of transactions for the channel, batch them according to configuration, and cut blocks that peers will later validate and commit. Transactions are then packaged into blocks. The ordering service waits until the channel's batching rules are met. Enough transactions, a preferred block size, or a timeout. These settings tune the trade-off between latency and throughput. Each block carries ordered transaction envelopes plus metadata, and each channel maintains its own independent block sequence. After distribution, peers still validate each transaction locally before committing valid results to their ledgers. When a peer receives a block, it does not automatically let every transaction affect ledger state. First, it checks that each transaction has the required endorsements from the correct organizations. Then it performs the MVCC check. The versions read during simulation must still match the current world state. If something has changed, the transaction is marked invalid. It remains in the block for auditability, but it does not update world state. After validation, the peer commits the block. The full block is appended to the blockchain log, including transactions marked invalid, so the audit trail remains complete and immutable. Then only valid transaction rights are applied to the world state database, keeping current queryable data clean. Finally, commit events are emitted so client applications and downstream systems can confirm processing and trigger their next actions. Fabric's transaction flow separates execution, ordering, and validation to strengthen trust. Proposals are simulated and endorsed before ordering creates blocks. Validation then enforces policy, protects consistency, and commits an auditable ledger update. With this foundation in place, we can now explore channels, private data, and confidentiality in enterprise collaboration.